Hello, this is Mr. Collier, and today we're doing proofs by induction. Okay, so this is how proofs by induction works. You start by showing it's true for n equals 1 or n equals some initial number. Then you assume it's true for a certain number k, then prove it's true for n equals k plus 1. And what that means is, okay, we know it's true for the first case. Then this shows that it's true for the second case. And it's true for the third case and the fourth case and so on. So it's true for all integers bigger than the initial case, right? So let's take a look at how this works. So in this example, we're trying to prove this. So we'll start with the first number called the base case, and this is z plus, so we're starting with the positive integers. So we start with n equals 1. So for n equals 1, we only have one term in this series. That's 2 times 1 minus 1 is 1. Okay, so the left-hand side of the equation is 1. The right-hand side is 1 squared, which equals 1, and those are the same, so therefore the statement is true for n equals 1. Now we go to the assumption. We have to assume that 1 plus 3 plus 5 plus basically the sum of the numbers equals n squared. For the assumption we're assuming n equals k, so we need to write k instead of n. So this is k squared for some k in z plus. Okay, now here is the next part where we look at k plus 1. So we'll just work with the left-hand side and show it should be equal to k plus 1 squared. Okay, so we're showing that if n equals k is true, then n equals k plus 1 also has to be true. So we have this. So if we have our last term of this series is going to be 2 times k plus 1 minus 1. So our previous term before that is just 2k minus 1. Okay, so this is what our series looks like for k plus 1. And notice at this part we assume that this equals k squared. So we can substitute in k squared for this. Okay, so k squared plus 2 times k plus 1 minus 1 by assumption. And we sometimes call this the inductive step. Okay, so what we want is to show that that equals n squared. We just expand it, and I think it's going to be k squared. So this is 2k plus 2 minus 1. This is k squared. It's 2k plus 1. So this is, if we factor it, is k plus 1 squared. So therefore, it is true for n equals k plus 1. Okay, and then you always need to write a statement at the end to state that this is true. So we say the statement is true, or let's say it's true for n equals 1. And if n equals k is true, then n equals, let's just rewrite this. If it's true for n equals k, then it's also true for n equals k plus 1. That's what we proved. Then it's true for all integers by the principle of mathematical induction. So then 1 plus 3 plus 5 plus dot 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 plus 2 n minus 1 equals n squared for all n in z plus by the principle of mathematical induction. Okay, we're going to look at a slightly different one now, but it's also a series. Okay, this should say maybe n is a z plus, so we'll start off at n equals 1. Okay, so n equals 1, the left-hand side is just going to be 1 squared, which is 1. The right-hand side is going to be 1 times 1 plus 1 times 2 times 1 plus 1 over 6, which is 6 over 6, which equals 1. Therefore, it's true for n equals 1. So now n equals k. Assume 1 squared plus 2 squared plus 3 squared plus and so on plus k squared equals k times k plus 1 times 2k plus 1 over 6 for some k in z plus. Next step, n equals k plus 1. Okay, we're going to start with the left-hand side with k plus 1 plugged in. So we have 1 squared plus 2 squared plus 3 squared. Now before k plus 1 there's a k squared. So let me write that in. And just like before, this whole part is what we assumed before, so we can replace that with k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. Now, that's by assumption. If we expand all this, we'll get k cubed, we'll get a cubic. It'll be a little bit hard to factorize. So before we do that, notice that we have a k plus 1 in both terms. So we can factor out the k plus 1. Inside the bracket, we're going to have 2k squared plus k over 6. And we need a common denominator, so this is 6k plus 6 over 6. And we'll add those together. And we'll get 2k squared plus 7k plus 6 over 6. And if we factorize that, actually let's put 6 under the whole thing. If we factorize this, we get k plus 2 times 2k plus 3. And if you look closely, that is just k plus 1. Yeah? This is the k plus 1 inserted into the right-hand side. So you can write it clearly like this. And it's k plus 1 plus 1. And this is the same as 2 times k plus 1 plus 1. Okay? Therefore, it's true for n equals k plus 1. And then we need our statement at the end. Okay, it's true for n equals 1. And if it's true for n equals k, then it's also true for n equals k plus 1. Therefore, it's true, or I can write the statement, 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared equals n times n plus 1 times 2n plus 1 over 6 for all n in Z plus by the principle of mathematical induction. Okay, next example we have proving this. This is the sum of a geometric sequence formula, it looks like. So we're going to prove that this is true. So this should also say for n in Z plus. So let's start with n equals 1. For n equals 1, the left-hand side is not just 1, it's we plug in 1 for the r, and we have just 1 plus r. Okay. The second term is 1 plus r squared. The third term is 1 plus r cubed. So now the right hand side, let's plug in 1. We get r to the power of 2 minus 1 over r minus 1. The numerator factorizes. So this is just r plus 1. Okay, so it's the same thing, so therefore it's true for n equals 1. Okay, next is the n equal k part. N equals k, assume 1 plus r plus dot 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 plus r to the power k equals r to the power of k plus 1 minus 1 over r minus 1 for some k in the integers. Okay, so then for n equals k plus 1 step, we do this 1 plus r plus r squared plus dot dot dot. We'll have an rk, and then we'll have an rk plus 1. Okay, then we'll just plug this in. So this is all just r to the k plus 1 minus 1 over r minus 1 plus r to the k plus 1 by assumption. Okay, and we want to add these together. We'll get a common denominator. This is plus 1 minus 1. So the common denominator, we have to have r minus 1 times r to the k plus 1 over r minus 1. And we'll add these together. This is going to be r to the power of k plus 1 minus 1 plus r times this is r to the k plus 2 minus r to the k plus 1 all over r minus 1. Okay, now this first term and the last term cancel. I'm going to rearrange these two, and we just have r to the power of k plus 2 minus 1 over r minus 1. Okay, so this is the same as r to the k plus 1 over r minus 1. So this is just the k plus 1 term. So this means, therefore, it's true for n equals k plus 1. And then we write a similar statement to what we did before.